All right, feel free to begin.
Okay, we still have your screen on here, Neil.
Oh, okay.
Yep.
So it's not the forest hydrology slide?
No, it's Google Maps or
Oh,
something like
sorry.
that.
Okay. Okay. There we go. How's that?
Perfect, thank you.
All right, you're welcome.
Okay. Welcome everyone. We have a few people just finishing up getting in here. So this is the second part of Advances in Forest Hydrology. We have two more talks. Yeah, Vaughn at 3:25 is not actually today. It has been moved. So that last talk there is not actually here. So to get us started with the second half, we have Matt Watkins. He's going to be talking about the effects of forest disturbance on water quality in the Algoma region in central Ontario. So Matt, you can take it away.
Okay, sounds good. I'll just share my screen here. So can everyone see that?
Yep.
Okay, sounds good. I'm just trying to move this little bar out of the way.
Sure.
But, whoops. Well, I guess I'll just have to run with it. So again, so yeah, my name's Matt Watkins. I'm a second year master's student at Trent University. And again, my project's looking at the effects of forest disturbance on water quality in the Algoma region of central Ontario. And just to start, I want to link some key background information together here, starting with the boreal forest. So the boreal forest is a very important and also very large ecozone in Canada, and primarily important due to its source water, what's the word I'm looking for here? Freshwater distribution to communities in the nation. But with great size comes susceptibility to disturbance events such as wildfire and harvesting, which are well known to affect many components of downstream water quality. And the one I want to look at today is the potential of increased levels or loads of dissolved organic carbon, or DOC, to our treatment facilities. Not only does DOC cause odor and discoloration in stream water, but the humic substances present also can react with treatment chemicals like chlorine to form disinfection byproducts, or DBPs, which have been somewhat linked to health risks in humans. And I just want to make this clear as well that DBPs do not drive treatment decisions. Things like algal growth associated with bacteria and loads of DOC are far more problematic from an economic standpoint. So the idea behind this project was to, get out into the interior of the shield and do sort of a landscape scale stream water quality assessment of numerous catchments. And the primary research question I had was, do certain aspects of forest disturbance have an effect on things like DOC concentration, the quality of that DOC, disinfection byproduct formation potential, and or the entire relationship between all of those. And ultimately, like, a lot of work has looked at this in terms of on the small scale in places like Turkey Lakes that I have on the map there. But the boreal ecozone is definitely lacking a scale of this size and magnitude. So in terms of that size, what I did was selected 30 catchments across 3 forest management units in the Algoma region. And these catchments were selected primarily based on recent disturbance criteria, and they range in size from just over about half a kilometer squared to just over 100 kilometers squared, so quite the range. And the breakdown is as follows. There's 14 control sites, there's 6 sites with mixed disturbance histories, 6 insect dominated sites, and 4 harvest dominated sites. And because this scale of the map is, kind of hard to see, I've tried to provide some context in the inset maps with relation to where I sampled and also where I took discharge with the little red circles relative to the catchment delineations and the highways that are kind of faintly there, but you can probably still see them. And lastly, one note that that scale on the bottom is not incorrect. It's that arc from starting from the Sioux all the way up to Wawa is about 325 kilometers in length. And sometimes I forget just how much distance I covered out there. And in terms of methods, I started by doing sort of a GIS-based catchment delineation and selection, And then accessibility also played a role with, selecting sites in terms of field visits. And infrastructure wise, it's, we don't really have any infrastructure out there. So I basically did a combination of stream and surface loggers so I could capture continuous stage over the period of about 5 months, and then revisited these sites every 2 to 3 weeks or so to take those discharge estimates and also take water samples. And I was lucky enough, by the grace of 4Water, to do some disinfection byproduct formation potential sampling at 8 of those sites with very different, they're kind of end members, very different disturbance histories, also a lot of landscape characteristic differences across those 8 sites. And I just want to be clear that when I mentioned DBP-FP, it's the naturally occurring precursors to the compounds that exist in the environment. And so one thing that pops out in terms of stream flow is the vast diversity in terms of water level patterns seen in this region. So what I have here is 6 sites with water level on the Y, and then the duration of the field season on the X. And as you can see, some of these sites are very responsive to localized precipitation events in the region, and they drastically, contrast with some of these lake or wetland associated sites where you get this, steep drop off in water level and slow recovery as you move into October. But probably the most interesting is the final column there of these increases where you have this restabilization of the water level at a higher water level rather. And one thing that I just did not take into account before I started this project was the influence of beavers and downstream damming and how that affects sort of like where I was taking discharge in the water level. And it's probably most evident with sort of that 3-tiered stabilization. And I believe that's Watershed 45 there, which is just sort of a fascinating variable that I really didn't think I would capture. And in terms of shifting over to some of the preliminary chemistry, this isn't really going to surprise many people, but the sites that have been disturbed are showing elevated levels of DOC concentrations, but the more interesting thing is the wide variation of the DOC concentrations in those 14 control sites. And this sort of links back to those different landscape characteristics in there. You have differences in slope. The catchment area varies a lot. Things like wetland cover goes from sort of 0 to 25% in there. And also canopy cover type, like deciduous tree percentage, varies widely in those sites. So as much as I would love to say a disturbance, as the smoking gun for, some of these treatability metrics, there's definitely more going on in the landscape. And speaking of treatability metrics, when we look at a few here in terms of trihalomethane formation potential and specific ultraviolet absorbance, you do see that same pattern where, disturbed catchments are having higher values. And excuse me, I just want to clarify that trihalomethane formation potential is just the precursor to the main disinfection byproduct seen at our facilities. And also specific ultraviolet absorbance is just a technique that's normalized for DOC, and it's relatively a good predictor of its chemical characteristics. So in short, low SUVA values, you're going to have more hydrophilic, labile DOC, and higher SUVA values, you're going to have higher presence of humic substances and also more refractory DOC in nature. And one of the last things I want to touch on is sort of the seasonal variability in some of these metrics. So for example, start with DOC. Even though it varies spatially, it's not really varying in any of these catchment classifications over time. Sample number here effectively acts as date, as sample 1 was taken in late May, early June, and sample 5 was taken in September. So as you walk across to the right, you're kind of traveling through the summer. But this pattern and story starts to change when you look at something like THM-FP, where for each of the classifications, you have something kind of, very different going on. For example, you have the control that sort of tapers off and sort of that variability around August, and also the insect dominated catchments. You have this sort of, step-like reduction in concentration, which is very interesting. And One thing to note here is that DOC concentration predicts THM-FP fairly well, but these concentrations may depend more on the unique organic composition of these surface waters and not just the DOC component. And when we look at SUVA across time too, there's almost like a regional pattern here of that sort of step reduction change around the August point if you disregard sort of the notable increase in value and variability in that fourth sample for the harvest sites, which is kind of interesting. And I would suspect that, this is some sort of regional control because you're kind of having a compositional DOC change around that, peak summer period. There's probably high temperatures across the landscape, very low water in these systems, which would, impact connectivity across these catchments. But at this stage, this is just sort of I'm just starting my investigation into, explaining these patterns and some of this variability. So with that, I'll just leave you with some sort of project checkpoint conclusions and next steps. So again, just to reiterate that DOC ranges widely across the region and especially in those control catchments. And it seems that disturbance, does play a role in elevating some of these important treatability measures such as DOC and SUVA and that sort of thing. But it's definitely not the entire story because as my third point kind of sums up here, those landscape characteristics are going to play a pivotal role in describing some of those, well, A, the variability, and two, some of those patterns as I dig deeper. And I'm still excited to, look at total disturbance binned in sort of time profiles, like does, looking at 2 years differ than, the response if we can include 10 years of disturbance in the catchments. And I also have a bunch of carbon characterization data that I can sort of tie into those landscape characteristics to get a better understanding of the DOC sourcing and the quality of that DOC in some of these catchments. And finally, looking at sort of instantaneous DOC load comparisons between disturbed catchments relative to nearby controls. Are there significant differences there? Are they outputting the same amount of DOC and that sort of thing? And so with that, I would just like to thank the 4Water partners that support this engaging and important research. And if you have any further questions, please reach out by email. And with that, I just thank you for listening, and I'll gladly stop talking now. So I'll turn it back to Sheena.
Thanks, Matt. I'll open it up to questions. Does anybody have any questions for Matt? Danielle, just open up the chat here. Yeah, great talk. Awesome to see your data worked up. You briefly mentioned looking at some longer timescales at the end of your talk here. How would you aim to do that?
Yeah, so I basically have an entire legacy disturbance history by year. So what I can kind of do is group those catchments in, only looking at disturbance since 2017, or I can, look at longer timescales like with disturbance back to 2012 or 2010 and sort of just bin those total disturbances instead of just looking at the specific like classifications, because as I kind of mentioned, the environment is really messy. There's, I kind of built the project on most recent disturbance, but each catchment has, multiple disturbances. You have like harvests on top of insect infestations on top of wildfire. So it'll, it's a big legacy data set, but I think I can, extract some interesting insights if I sort of look at that temporal profile of the disturbance.
Yeah, I think that would be very useful, and knowing the whether between the disturbances there's equal time since disturbance as well. Any other questions? May have time for another short one.
Yeah, just then a quick follow-up on this topic. Yeah, how recent are the disturbance in the disturbed sites, and do you think that play a major role in your water quality results?
Yeah, so it kind of depends on the catchment. Most of them, I started with a timeline of, okay, let's let's just look at disturbance within 5 years, so those are all included in sort of those catchment classifications. But I was running into issues with, I have a low amount of harvest dominated sites, and I kind of, what's really interesting is there's not much wildfire in the region either. So I had to open up that disturbance window, back to 10 years and 13 years to capture the amount of sites that I wanted. But when I'm kind of just on the cusp of this, like, you might have more significant effects if I only include 2 or 3 years of disturbance in terms of recency. And we might not even be seeing any effects if I include, sort of a mixed palette of 10 years of disturbance. So give me a couple of weeks and I can get back to you with that. So.
Sounds great, yeah.
All right, thanks, Matt. Up next, we have our second and last speaker for our session. We have Will Fines. Will here, there you are. Yep. So Will's going to be presenting intermediate and legacy impacts of different harvesting strategies on phosphorus yield in upland hardwood forested watersheds. Okay, take it away.
Perfect. Okay, everyone can see that? Perfect. Thanks, Gina. Well, hello, everyone. My name's Will Fines. I'm a master's student at the University of Waterloo, and I'm going to be talking today about the immediate and legacy impacts of different harvesting strategies on phosphorus yield and concentration. I'd like to take a second to quickly acknowledge my supervisor, Dr. Mike Stone, as well as the other co-authors who have been integral to this work, Kara Webster, Jason Leach, Jim Buttle, and Monica Amelko. And so forested watersheds are known for their critical importance in the safe provision of drinking water supply around the world. And they save us over 4.1 trillion US per year to drinking water treatment costs and provide over 88% of Canadians with their drinking water supply. And so this just shows how important this forests are and the importance of understanding how disturbance impacts them. And disturbances are known to impact the forest's watershed's capacity to provide safe drinking water through increased transport of sediment and nutrients, such as phosphorus. And as the disturbance I'll be focusing on is harvesting. And now lots of studies have looked on the immediate effects of harvesting less than 10 years, but much fewer have looked at the legacy of impacts greater than 10 years. And then that is what I will be looking at. So my objectives will be to evaluate the immediate and legacy impacts of different forest harvesting strategies on total phosphorus concentration and yield in a hardwood dominated upland forest at Turkey Lakes Watershed. And then I'm also going to compare and see how Turkey Lakes, or the harvesting effects at Turkey Lakes, compares to other harvesting experiments around the world. So as Annie Gray described, Turkey Lakes Watershed is about an hour and a half northwest of Sault Ste. Marie, Ontario, and it's located on the Algoma Highlands. It's hardwood dominated, mostly sugar maples, and is characterized by high relief with thin soils, and is a series of lakes interconnected by small headwater streams. And the catchments I will be looking at are 31, 32, 33, 34, 35, and 46. And in 1997, 31, 33, and 34 were harvested with a clear cut, selection cut, and shelterwood cut harvesting treatment. And it should be noted that selection cut and shelterwood cut are typical harvesting strategies for these forest types. And the clear cut was just included to have kind of a worst case for an extreme harvesting or disturbance intensity. And now the water quantity and quality record spans from 1981 to 2012. And using a before-after control impact study design gives me 16 years of pre and 14 years of post-harvesting data. So I've taken this historical data set and I'm summarizing either concentration or total phosphorus yield data points down to an annual seasonal flow-weighted total phosphorus concentration or total phosphorus yield. And just what I mean by annual seasonal is for any year, there are 4 data points, 1 for each season. And then once the data summary is complete, I've created these calibration regressions, which can be seen on the right here. These ones are just happen to be for total phosphorus yield between all 3 controls and then the 3 harvested catchments. And these regressions are created with the pre-harvesting data, so no disturbances occurred in the harvested catchments. And then once these regressions have been created, they can be used to predict what should occur in those harvested catchments as if disturbance had not occurred. And when you have predicted values, you can compare them to the observed. The observed minus the predicted is just the harvesting effect. The Mann-Whitney U and ANCOVA tests were used to test for significance. And then I also look at the range of differences between those observed and predicted values pre and post harvest, and also the ratio of positive to negative values. And so this figure right here shows the harvesting effects on total phosphorus concentration. And I'm going to take some time right now just to explain it, as there is a lot going on. So on the x-axis, that's just time in years, or water year. And then on the y-axis is the effect of harvesting, or the difference between those observed and predicted values in micrograms per liter. The black vertical line represents the time of harvesting. So everything on to the left of these lines is pre-harvesting conditions, and everything to the right is post-harvesting. The dashed black lines represent that maximum and minimum difference between the observed and predicted values before harvesting occurred. And so if you were expecting a strong or a large harvesting effect, you would expect to see a lot of values over top of these black lines in that post-harvesting period. Columns represent the different control catchments, 32, 35, 46 on the right, and then rows represent the different harvested catchments, clear cut up top, selection in the middle, and shelterwood down below. And the first thing I'd like to point out is that if you look at the kind of the magnitude of the harvesting effects in these post-harvesting periods, they're all relatively small, ranging from around 1 to 2.5 micrograms per liter, which in terms of, I guess, like an increase in phosphorus concentration is small and unlikely to have a negative impact for downstream aquatic environments. And this is also confirmed when you look at, there are very few points that get above these dashed lines. You have a couple of outliers in the clear cut, one in the selection cut, and one in the shelterwood cut. And then also confirmed again by the change in this ratio of positive to negative differences, with the largest change going in the clear cut of 1.26 to 2, for the selection 0.85 to 1.6, and in the shelterwood cut, that ratio decreased. And the ratio just provides, I guess, if you didn't have a very large difference, but a consistent increase in phosphorus, the ratio will represent that. And so when you look at the same figure for total phosphorus yield, you see a slightly more of a harvesting effect. Magnitude of effects are ranging from around 5 to 10 grams per hectare over a season, which still isn't a lot of phosphorus, but then much more than when we saw for total phosphorus concentration. You again don't have a lot of points that are getting outside of that pre-harvesting range. But when you look at that ratio, it is increased dramatically in all harvested and control comparisons, with the largest increase going from 1 to 11 for the clear cut, 1 to 16 for the selection cut, and 1 to 8 for the shelterwood cut. So there's definitely much, I guess, a larger or a more consistent response of total phosphorus yield than there was to total phosphorus concentration. The last two things I'd like to point out on this slide, first is that if you look at all the first 3 years in these harvested catchments, you don't seem to see much of a response, and that is consistent throughout all of the harvested catchments. And I'm assuming that's due to 3 very dry years that occurred immediately after harvesting. The next thing is comparing the clear cut and the selection cut, kind of are of extremes. The clear cut was the most heavily disturbed, the selection cut the least. They seem to be fairly comparable. The clear cut has higher maximum effects on harvesting yield, but the selection cut responds more consistently, which is surprising. And now when we look at some of the, I guess, the results from these statistical tests, these tables for concentration and yield show the results from the ANCOVA test, and then just those mean annual seasonal harvesting effect values. And again, as not surprising, only the clear cut responded significantly when compared to all controls, and the selection cut responded when only compared to C35. But while these values may be significant, I'll point out again, the mean annual seasonal harvesting effect is small, ranging from like 0.1 to 0.9 micrograms per liter. So unlikely to have any negative impacts on downstream aquatic environments. And then when you look at total phosphorus yield, you see a more consistent response with all harvesting catchments showing a significant increase when compared to all controls, and your mean annual seasonal harvesting effects ranging from around 1 to 3 grams per hectare. And again, I'll point out how similar the clear cut and selection cut, which is surprising just since they have such a difference in disturbance type. But then, so comparing to other harvesting effects from different studies, I've taken these mean annual seasonal harvesting, or not the mean, the annual seasonal harvesting effects and summed them up for each year to get an annual effect, and which ranges from around 0 to 20 grams per hectare for the 3 harvested catchments. And when you compare to some of the studies coming out of Sweden and Finland, you can see that we lie right within the range. These studies found ranges from around 2 to 40 grams per hectare, and we are right in the middle of that for our maximum harvesting effects. However, when you compare to some of the other experiments that are getting up to 100 or 1,000 grams per hectare increase in phosphorus yield, it leads to the question, well, why is there such a limited response on these environments or at Turkey Lakes? And that could be because of just environmental conditions, climate conditions, but it could also be due to the fact of differences in the disturbance type or experimental design. Some of these study sites included site preparation, fertilization, road construction, which have all known to increase phosphorus concentrations on the landscape or increase rates of erosion, which is can transport lots of phosphorus downstream. And as Turkey Lakes doesn't have some of those disturbances, we may be missing potential effects. And I'll also note that another reason why maybe the selection and the clear cut are so comparable, there's one kind of ATV track that runs through the selection cut that may have increased erosion to the stream channel. So quickly to conclude, there's small significant increases in both total phosphorus concentration and total phosphorus yield, with the yield responding more consistently than concentration. As these increases are so small, they're unlikely to have negative impacts on downstream aquatic environments or hamper drinking water treatment operations. However, more work is definitely needed to confirm that. The largest harvesting effects were occurred 3 to 9 years after disturbance, surprising as you expect the largest ones to occur in the first 3 years, but that's likely due to those extremely dry years immediately after harvesting take place. As phosphorus yield responded more than concentration, it's safe to assume that it's being driven by changing hydrological conditions and not changes in phosphorus availability on the landscape that would increase concentration. And finally, impacts at Turkey Lakes watershed are small when compared to similar harvesting experiments, but an asterisk should be attached to that as we may not have included extensive road networks or larger catchments that may have shown a larger impact. Some of my next steps are going to be, is there still an impact 20 years afterwards? And what, if there is or if there isn't, why aren't we seeing an impact? And trying to understand some of the underlying processes that are occurring on the landscape that may be limiting the response of phosphorus. And I've done this through a field season that was conducted last year, where we measured phosphorus from numerous different source areas and collected some high frequency water chemistry data from the streams there. I would like to thank the For-Water Network and for funding this work, NSERC, University of Waterloo, and all of the academic, non-academic partners. And I'm happy to take any questions.
Great, thanks, Will. You can open it up to the audience. Does anybody have any questions for Will? Danielle. I might have missed this, but why do you think the largest effects didn't show up until 3 years post-harvest rather than in years 1 or 2?
So my best guess is those first 3 years were incredibly dry. It was as soon as they cut, everything got much drier at these sites. And I expect that that as there was so much less water flowing through these systems, despite the harvest, there just wasn't any moving water to transport stuff off the landscape. So that's my best guess.
Great. Any other questions from the audience?
Yeah, just basically a follow-up to that. Do you think because the streams are kind of smaller, if you had, like, if you're near larger streams with less ephemeral flow, would you think you would see more response?
Potentially. I think with larger catchments, you maybe have like more of an extensive disturbance type, so more road networks, more landings, and those other features on the landscape. And I think those are the real cause of any impact on phosphorus, just because it increases erosion and sediment transport to the stream. That would be my best guess. It is, yeah. And it's just that these smaller catchments don't have those intensive, those other harvesting related infrastructure features.
Yeah, great.
Okay, so if there's no other questions, I guess we'll be wrapping up our session. So I'd just like to thank all of our presenters and the audience for coming out to our sessions. On behalf of myself, Magali, and Jason, thank you all very much.